Hey, have you ever experienced deadlock and still wants to keep granting resource requests when possible and check for deadlock presence and take action for recovery? Fret not, deadlock detection method is the way. So there are three methods to handle deadlock. We have prevention, avoidance, and detection. So as we go up from the bottom of the pyramid, we have a lot of more restrictions. Meanwhile, if you go down from the top of the pyramid, the processing time is taking much more longer. So, prevention and avoidance are preemptive because you have to allocate the resource amounts before you copy the answer program. But for detection, it is responsive because it will give you resources while they can and check for deadlock for each time they want to allocate resources. So, how does deadlock detection works? Ooh, I know, I know, I know, ooh, I know. Roll the drum rolls, please. Basic algorithm. A check for deadlock can be made as frequently as each resource request or less frequently, depending on how likely it is for a deadlock to occur. So, first and foremost, we have to mark processes in allocation matrix that contains all zero elements. In this case, it is P4. And then initialize a matrix W equal to available matrix. Look for processes in request matrix that satisfies Pi. In this case, it is P3. To calculate the new temporary vector, first we have to add the old temporary vector with the allocation matrix in P3. And then we look for other processes that satisfy the temporary vector. In this case, P1 and P2 does not satisfy the temporary vector. So, what does that mean? Process 1 and process 2 in request matrix are unmarked. Thus, the cycle is in deadlock state. No. No.
But not to worry, we have a solution. Here, let me make it simple for you. Imagine the machines are the processes and the boxes are the resources. So, machine B must wait for machine A to finish its task before it can begin its own processes. Deadlock happens when all the processes wait for each other to finish. So, these are some of the strategies that is needed for recovery. Number 1. Abort all deadlock processes. This is where you simply turn off all the machines so it does not continue to work. Number 2. Back up all deadlock processes and restart. All we need to do is to save all deadlock processes at each checkpoint and restart it from there. This requires that rollback and restart mechanisms be built into the system.
Third strategy is successively abort deadlocked machines until deadlock no longer exists. The order in which machines are selected for abortion should be on the basis of some criterion of minimum cost. After each abortion, the detection algorithm must be re-invoked to see whether deadlock still exists or not. I have a question. What process should be selected to abort? Let me explain it. Firstly, the least amount of processor time consumed will be selected to abort. Machines that have consumed the least amount of processor time might be terminated first as they have the least impact on overall production. Secondly, the machines that have produced the least output might be chosen for termination or pre-emption, so that the upper machine will be selected to abort to minimize the loss of completed work. Then, the third criteria is lowest priority. Machines with the lowest priority might be chosen for termination or pre-emption to ensure that higher priority tasks are completed first. The last strategy is successively print material until deadlock no longer exists. As in me mentioned just now, a cost-based selection criteria should be used and re-invocation of the detection algorithm is required after each pre-emption. A machine that has a material printed from it must be rolled back to a point prior to its acquisition of the material. That's all for our animation. Thank you.